And welcome to this IB Explainer video on electric current. We're going to look at two equations of electric current. One of them fairly simple, and we'll look at a couple of examples of how we use it. And the other is a little bit more involved. It's a derivation of a more advanced equation, which is given in the IB data booklet. Okay, let's get starting with our definition of what electric current is. Current, well, in any definition, is really to do with flow. So when we have a river flowing, we can talk about the current moving. In electric current, we're talking about the current which is formed when a charge moves. Now, in terms of an official definition of current, the quantity current, we say that current is the rate of flow of electrical charge from one location to another. That definition leads to our first equation, which is a really simple one, which is our I current is equal to delta Q over delta T here. Delta Q is the charge, and delta T is the time. Q is the charge which flows past a particular point during our time delta T. We can do a bit of dimensional analysis. The units of current are amps. That's one of our SI base units. And 1 amp is equal to 1 coulomb. That's the unit of charge per every second, which is our SI unit of time. Let's look at a couple of examples then. Firstly, we can calculate the current in a wire through which a charge of 25 coulomb passes in 1500 seconds. Well, all we have to do is apply our equation I equal to delta Q over delta T. We know that delta Q is 25, and we know the time is 1500, and so that we end up with a number of 0.0167 amps. I've given that number to 3 significant figures there, and I've remembered my SI unit of current. You could, I suppose, leave this as coulombs per second. However, that is not a base unit, so try to use amps where possible. Our second question is slightly different. We're given the current, 36 milliamps, that's 36 times 10 to the minus 3, and we want to calculate the charge flowing along the wire in 1 minute. Well, we'll start from the base equation here, I equal to delta Q over delta T, and we can then rearrange so that delta Q is I times delta T, and this is something which you are asked to do quite often. A multiplication rearrangement should be fairly simple for IB level. It remains then to put in the numbers. Okay, remembering that milli is 10 to the minus 3, and 1 minute, well, we're normally working in seconds as our base unit, and so therefore we're going to have to change that 1 minute into seconds, that's 60 seconds. So we'll take my 36 milliamps, multiply by 60 seconds, and again, we're left with 2.16 coulombs. As I've said, that's really the basic idea behind electric current. It really measures our flow of charge through a circuit or just through any electric field. What I want to turn our attention to now is a derivation of a much more complicated equation, which you're expected to use at IB level, and I hope that this is clear. Please do pause the video at any time if you think that there's maybe a bit too much information. It's quite involved, there's a lot of variables we need to define. However, the outcome is a fairly simple one to apply. Okay. First things first, we're going to apply an electric field. You can see a positive and a negative in the screen. That's going to be important later. We're applying that electric field to a cylindrical wire. And I'm going to say that my wire has got a length L, not to be confused with I here, this is L, and a cross-sectional area A. Okay, so therefore has a volume equal to A times L, and we'll use that later. Now inside my wire, a wire is a conductor, there are going to be lots of charges. And we've just said that electric current is the movement of those charges. Okay, here we're looking at conventional current, and conventional current is the flow from positive to negative. Now, when our charges flow, they don't actually flow in a straight line. They flow in a kind of zigzag way similar to Brownian motion, and their net movement is from positive to negative. Here we are assuming that we have got positive charge carriers, and so therefore we've got our charges which are moving in a resultant way from left to right. Okay, so we've got current moving from left to right. Now, why are we doing this? What we want to do is we want to use these facts to develop an understanding of what's going on inside a wire when current changes. Okay, and what are the variables that we can control in order to change the current going through a conductor. So let's get started with that. We first start off with the fact that the volume of our wire is equal to A times L. That's going to be important a little bit later. Okay. Now, the reason we want to know the volume is because we define a new quantity N. Okay, I will note down what N is in a second. N is something called the charge density. And all that says is how many charge carriers I have per unit volume. Okay, now each of my charge carriers, in this case, my little orange things, each little charge carrier carries a charge Q. And I'm gonna assume that the current is due to the movement of those charges from positive to negative. Well, in my case, I have 7 charges on the screen, and so the total charge moving from left to right is going to be 7 times small q. Now obviously, when we're dealing with a wire, we're dealing with a lot more charges. Okay, we're dealing with thousands, millions, if not billions of small charges. Okay, so we can't simply count them up in that way. However, what we do is we take this number n, which is the charge density. Again, that's the number of free charge carriers that we've got, and multiply it by the volume to get the number of carriers. We then multiply the number of carriers by the charge on each carrier to get the total charge. That's what my second equation says. It says delta Q is just the free charge density times the volume times small q, the charge on each carrier. And then we've substituted my top equation in, V equal to AL, into the bottom one. So we've got delta Q is equal to my number of charge carriers per unit volume times the area times the length and times Q, which is the small charge on each of those carriers. That's really the complicated bit. That's why I've taken a little bit of time to kind of just labor the point there. We're obviously going to do this now. We're going to take my definition from the previous slide, I equal to delta Q over delta T, and we're substituting in. So we've got delta Q is that N times A times L times Q over delta T. Why is that important? Well, we notice there we rearrange a little bit. We can take my L to the end of the equation, my delta T, we've got a distance divided by a time. That allows us to define a new variable, which is simply V. Okay, V is a velocity, or in some cases a speed. And here we're really looking at a kind of an average speed. We therefore end up with an equation which is very well known, which is our current is equal to N times cross-sectional area, A times Q times V. And I want to talk about what each of these variables are now in a bit more detail. Obviously, current is the rate of flow of charge. A is the cross-sectional area of my wire. So you can see there that if I make my cross-sectional area of my wire bigger, then I can make my current bigger. And the reason for that is because there is more surface area for the charge carriers to flow through. N, and I'll repeat this, it has a number of different names, you'll have heard me use them already, is the number of free charge carriers per unit volume. In other words, it's the number of, say, for example, in a wire, the number of electrons that I have available in order to do the conducting. Okay, free charge carriers could be any type of charge, could be electrons, could be protons. As long as they are free and available to join in the flow of current, then they are counted as free charge carriers. And here we've just said that they are the number per unit volume. Now this per unit volume is the reason as a result of having this per unit volume, we often refer to this as a charge density. Okay, you should know that density is mass divided by volume. Here we've got number of free charge carriers per unit volume. And therefore it has the unit meters to the -3. It's a slightly weird unit, but this comes from the fact that our number doesn't have a unit. Okay, number is just a quantity. Okay, however, per unit volume definitely has a unit that is meters to the minus 3. Our Q is simply the charge on each charge carrier. And as I've said, our charge carrier could be any type of charge carrier. It could be an alpha particle, could be a beta particle. Okay, as long as it is charge, then we can have a charge carrier. Typically, we are dealing with electrons, because the situations where we'll be looking at charge flow and applying this equation usually would apply to an electrical wire, and the charge carriers in an electrical wire are electrons. Just be aware that there could be other ones, and those are more sort of hypothetical situations. The charge on each charge carrier is measured in coulombs. The last one is this V that we kind of made up at the end. I want to give a more formal definition. This is the mean drift velocity, okay, of the charge carriers. Now, the reason we call it a drift velocity, drift usually implies quite slow. And as we'll see, as I'll state in a second, the drift velocity is actually fairly slow. The electrons are moving fairly fast, but as you can see, they're moving in different directions. Okay, as I made the reference to Brownian motion, this idea where we're kind of changing the direction. And the result of this is that actually electrons move fairly slowly through a wire, or charge carriers in general move fairly slowly. So therefore, we define this mean drift velocity. It is the total the distance essentially moved in between our positive and our negative, divided by that time. Okay, it's the length of the wire divided by the time. Obviously, the faster the drift velocity, the higher the current. Okay, so we've got these 4 quantities. Our current is directly proportional to all of them. So as I've said before, if we increase the cross-sectional area, we have a greater current. If we increase the number of free charge carriers per unit volume, we increase our current. If we increase the charge on each charge carrier, we increase the current. And if we increase the speed of them, we also increase the current. A couple of small notes to finish. One, we can use this equation, and I think its most sort of useful application is to distinguish between materials. You should be aware that we have 2 types of materials generally. We have conductors and we have insulators. Using this equation, we are actually able to distinguish between the 2. In a conductor, we have a high number of N. Okay, the main difference between conductors and insulators is the fact this number of free charge carriers is different. Okay, you should know that conductors have a lot of free electrons, and so therefore N is going to be very high. Insulators, however, have a low number of free charge carriers, not 0, however low, and so therefore the current flowing through them is also going to be low. Now interestingly, as we'll study later, there's also material which is called a semiconductor, and that is one for which N changes. Under certain conditions, N is very low, and so the material is an insulator, and under other conditions, N is very high, and so it is a very good conductor. Okay. A last point, V, our drift velocity, is typically very, very small. It's typically of the order of millimeters per second. So when you're using your equation to calculate, and you're asked to calculate drift velocities, do not expect high values. We often have the idea that electricity travels at the speed of light. Well, actually, electric current does not travel at the speed of light. Okay? Electric current travels relatively slowly in terms of the drift velocity. What is fast is the speed of the signal which we send between our conductors using electric and magnetic fields, and that's something for us to discuss at a later date. That brings us to the end. Okay, do take some time to have a look at the derivation of that equation. It will be one that you're expected to use in your examinations. And as ever, please do let me know if there's anything which is unclear. I'm always happy to explain it to you in further detail. Thanks for listening.